So a black hole is an object that's so dense and so massive that it has gravity so strong that nothing can escape, not even light. And these are typically formed when a star reaches the end of its life and collapses. And in this case, what we found was a star that got too close to a black hole and it got torn apart. So this is actually very similar to the way that the moon tugs on the Earth and creates tides in our ocean. What happens is the star gets too close to the black hole and it gets stretched out by the tidal forces from the black hole. This causes it to be torn apart into a long stream of material that then gets blown out and falls back onto the black hole, creating a lot of hot material that we can observe. And because it involves tidal forces, we call it a tidal disruption. So this is a great story of collaboration between different groups here. So I am part of a group called the All-Sky Automated Survey for Supernovae, or SASN. We are a network of small telescopes on the ground, and we discovered this event. And we then triggered SWIFT observations with NASA's SWIFT satellite in the UV and X-ray. And we did this because we knew it was being monitored by NASA's TESS satellite, which only beams its data back to Earth every couple of weeks. So combined, we ended up with a really nice multi-wavelength data set for this object. So we learned a couple main new things from this event. And the first of these was, because it was already being monitored by TESS at the time, we had data going back for months. Every 30 minutes, we had gotten an image of this area of the sky. So we were able to see exactly when it started to get brighter and exactly the way that it started to brighten. The other interesting thing that we found is that using SWIFT, we were able to fit its temperature, and we found that it was actually getting cooler early on, which is really unexpected for one of these. We've never seen that before, and honestly, we're not exactly sure what causes it, but we're looking into that now. So this black hole is about 375 million light years away, so it's definitely no danger to us. And actually, no black hole is, at the moment, any danger to the Earth. We're about 26,000 light years away from the supermassive black hole in our own galaxy, and you need to get very close to have any effect on the star, like in this case. So we're not in any danger, and we won't be for any time as long as we know. That's a good question. Black holes themselves are black, but they're often surrounded by a lot of gas, and this gets very hot because the black hole's gravity is acting on it. And so we can see the light from this hot gas. Sometimes they also launch jets of charged particles that we can detect. And they can also have events occur like a tidal disruption, where we can see the star falling into the black hole for a year or even more and observe them in that way. If you want to learn more, just take a look at NASA's Facebook and Twitter page at NASA Universe. You can also check out the hashtag Black Hole Week on Twitter for more information about this event and other black hole related phenomena. So what TESS is doing when it's looking for planets is it's looking for something that we call a transit, where a planet passes right in front of a star. This causes its light to dip for a short period. And in order to find these, you need to look at the same part of the sky repeatedly for a long period of time. So TESS is looking at every chunk of the sky for 27 days at a time. And what happens is that because TESS has a very large field of view, other things can be happening in the background while it's looking for these planetary transits. So that's how we were able to find this tidal disruption event, and also we've been able to use TESS to observe a number of supernovae as well. So this is actually a really interesting story. I happened to be observing in Chile at Las Campanas Observatory using larger telescopes to get follow-up data on some other discoveries that SASN had made. And we got our discovery trigger from South Africa. So I was able to train a larger telescope on this less than a day after we discovered it. I was also able to ask SWIFT for observations, and they responded very quickly. So we were able to get SWIFT data within 2 days of our discovery. And we were able to keep following it up with a number of telescopes while TESS was still observing it, and then we got the TESS data a little while later when it finally beamed that all back to Earth. So we ended up with a really nice multi-wavelength data set because of this really good cooperation between all these groups. Well, the reason we look at things so far away is because a lot of astrophysical phenomena, like tidal disruption events, are pretty rare. They only happen once every 10,000 or 100,000 years or so in galaxies like our own. So we really can't observe them in our own galaxy, and to do this, we have to look outside of our galaxy and look much farther away so that we can look at a lot of galaxies at once to find one happening. Thankfully, they're very bright, so we can see them very far away. Using our telescopes and also using much bigger ones, you can look even farther. So it's very similar to the way that we observe supernovae in other galaxies as well.